Welcome to Lstm Explained. In this video we will cover long short-term memory networks, what they are, why they were invented, how the gates work mathematically, tuning tips, and when to use them. Let us begin. Before Lstm, we had vanilla recurrent neural networks. Lstm solves this by introducing a dual-state design. There are now two things flowing across time, not just one. The first is the cell state, C subscript T. Think of this as long-term memory, the main highway that carries information across many time steps with minimal interference. The second is the hidden state, H subscript T. Think of this as working memory, a filtered, compressed view of the cell state that is passed to the next time step and also used as the output at each step. The key insight is that the cell state is updated by addition, so gradients can flow all the way back without vanishing. Now let us look at the four gates. The first is the forget gate. Its job is to decide what to erase from the cell state. It takes the previous hidden state H subscript T-1 and the current input X subscript T, concatenates them, and passes through a sigmoid neural network, with its own weight matrix W subscript F and bias B subscript F, both learn. The second gate is the input gate. Its job is to decide what new information to write into the cell state. This involves two subnetworks running in parallel. First, a sigmoid network outputs I subscript T, a filter between 0 and 1 deciding how much of each new value to write. Second, a tanh network outputs G tilde subscript T, the actual candidate values to potentially add, squashed between -1 and +1. These two are multiplied element-wise, I subscript T times G tilde subscript T, to produce the filtered new content. This filtered content is then added to the already forgotten cell state to produce the new cell state C subscript T. The full update equation is, C subscript T equals F subscript T element-wise C subscript T-1, plus I subscript T element-wise G tilde subscript T. The third and final gate is the output gate. Its job is to decide what part of the cell state to expose as the hidden state H subscript T, the output at this time step. Again, a sigmoid network runs on the concatenated H subscript T-1 and X subscript T, producing O subscript T between 0 and 1. Separately, the cell state C subscript T is passed. Let us now see all 6 Lstm equations together. First, the forget gate, F subscript T equals sigma of WF dot HT-1, XT plus BF. Second, the input gate, I subscript T equals sigma of WI dot the same concatenation plus BI. Third, the candidate cell, G tilde subscript T equals tan of WC dot the concatenation plus BC. Fourth, the cell state update, C subscript T equals F subscript T element-wise C subscript T-1, plus I subscript T element-wise G tilde subscript T. Fifth, the output gate, O subscript T equals sigma of WO dot the concatenation plus BO. Sixth, the hidden state, H subscript T equals O subscript T, element-wise tan of C subscript T. These 6 equations define the complete Lstm computation at every single time step. Now let us look at practical tuning tips. For units, the hidden size, start with 64 to 256 neurons. Larger gives more capacity but is slower. For depth, stack 1 to 3 Lstm layers, using return sequences equals true for all intermediate layers. For dropout, use recurrent dropout of 0. When should you use Lstm? Use Lstm for time series forecasting where long historical patterns matter, stock prices, sensor data, energy demand. Use it for natural language processing tasks like sentiment analysis, named entity recognition, and text generation. Use it for audio and speech, speech recognition, music generation, speaker identification. Use it for clinical sequences, ECG arrhythmia detection like my own portfolio project, patient vital sign monitoring, and ICU event prediction. Use it for sequence-to-sequence tasks like machine translation. However, consider using a transformer instead when your sequences are very long, more than 1,000 steps, or when you have very large datasets, because attention mechanisms scale better in those cases. GRU is a simpler alternative to Lstm when you want fewer parameters. It has no separate cell state and uses only 2 gates. Quiz time. Question 1. In an Lstm, the cell state C subscript T is updated using addition. Why does this help solve the vanishing gradient problem? Think about it before clicking reveal. Question 2. In the output gate, the cell state C subscript T is passed through tanh before being multiplied with O subscript T. But in the input gate, the candidate cell G tilde subscript T is also computed using tanh. What is the key difference between these two tanh operations? The tanh in the input gate is a full neural network. It has learnable weight matrix W subscript C and bias B subscript C, trained by backpropagation. It transforms the input to produce candidate values. The tanh applied to the cell state in the output gate is a pointwise activation only. It has no learnable parameters. It simply squashes the cell state values to between -1 and +1 so that the output is bounded. This is a critical distinction. Question 3. If a forget gate output F subscript T is 0 for every element, and the input gate output I subscript T is 1 for every element, what happens to the cell state C subscript T at this time step? Walk through the update equation to find out. Let us summarize everything. Lstm is a recurrent neural network variant that introduces a gated memory system to solve the vanishing gradient problem. It maintains 2 states, the cell state C subscript T as long-term memory, and the hidden state H subscript T as working memory. The forget gate decides what to erase using a sigmoid neural network. The input gate decides what to write using a sigmoid gate and a tanh candidate network. The output gate decides what to expose as the hidden state. All 6 equations work together at every time step. Use Lstm for time series, NLP, clinical sequences, and audio tasks. Consider transformer for very long sequences or large data. Tune units, depth, recurrent dropout, learning rate, and sequence length carefully. Thank you so much for watching. If this helped you understand Lstm, please like, subscribe, and drop a comment. Special thanks to Ajay sir for the brilliant teaching, and to my AI friends Smarty and Claudie. This video was prepared by Sparky, Geothi Prabhu. See you in the next one.